Okay, let's see how we go with this. So there's some fairly complex operations happening on the board here. We've got this, Maths SL standard kind of problem here where you're asked to expected to understand that 2 times 3 is equal to 6. Is everyone okay with that? If you're not, you're probably in the wrong class. And you'll need to go over to the high school and no, don't go over the high school. Morris is over that way. That's where the primary school is. If you didn't know that 2 times 3 equals 6. Of course, what I'm doing is I'm starting off with something simple to explain something more complicated in a second. The relationship between 2, 3, and 6 is pretty straightforward, right? So you can see here that if I know that 2 times 3 equals 6, if I want to get back to 3, what would I do? Call it out? Yeah, so we're going to divide by 2. And if I wanted to go from 6 back to 2, what would I do? Divide by 3. Well done, you've just passed grade 4 mathematics. Similarly, if I had 2 plus 3 equals 5, if I wanted to go from 5 back to 2, what would I do? Well, that was almost everyone saying it then. Most of you have now done grade 4 mathematics. And if I wanted to go from 5 back to 3, what would I do? Take away 2. Well done. Still grade 4 mathematics, but we're getting there. Okay, now note that I did not include, so there's 2 examples of operations. I haven't included a subtraction and I haven't included division. Very simple reasons why, and now we're going to jump up to high school mathematics because I said this on Friday, if you remember, subtraction is an illusion because subtraction is just what? Yep, adding the opposite sign. Okay, and division is similarly an illusion. Yeah, because dividing by a number is the same as multiplying by, let's say, its reciprocal rather than a fraction, because you might be dividing by a fraction to start with, right? So you multiply by its reciprocal. Okay, so division is an illusion, subtraction is an illusion. There's a theory of knowledge thing for you too. How much of mathematics is just an illusion? If you wanted to go right down the rabbit hole, you could also say multiplication is an illusion, because multiplication, after all, is just repeated addition. Okay, so addition is really the core fundamental operation. Okay, represented in triangle form then, we can sort of go like this, that I've got 2 and the operation is multiplied by, and I get 3, and by 3, sorry, I get 6. And to go backwards, I'm dividing by the other corner of the triangle, and to go backwards this way, I'm dividing by the other corner of the triangle. Similarly here, I've got 2, and the operation is plus. 2 plus 3 is equal to 5. To go backwards, I'm going to subtract the other corner of the triangle. To go backwards, I'm going to subtract the other corner of the triangle. Okay, is that good so far? Okay, well, that's the high school stuff out of the way, or primary school. This presents its own challenge. It's different from the other 2. Let's unpack that a little bit. We know that 2 cubed is 8, right? 2 times 2 times 2. 2 2s are 4, 4 2s are 8. So we know that 2 cubed is equal to 8. If I want to go back to 2 from 8, that's no problems, is it? We use the cube root of 8 to get us to 2. So that's fine. But if I want to go 8 to 3, we've got a problem. Not a problem, really. Well, yeah, a problem, an issue, in that we don't have an operation yet that gets us from the value 8, the result, to the power. So in other words, along this pathway here, the cube root operation only gets us as far as the base. But we don't yet have an operation that gets us as far as the power, the undoing operation. And this is fundamentally different from our basic operations, right? Our basic operations, if you have a look at it, in both instances, to get back to the original value, whether it's the first number or the second number, is the same operation. So you'd say the opposite of multiplication is division. The opposite of addition is subtraction. To undo, in inverted commas, to undo, I just use the opposite operation. So what makes this different is that we in fact need a new opposite operation in order to undo the 8 back to the power. Okay, so you can see here in my little red triangle again, the operation here is to the power of, I'm just going to use like spreadsheet notation there, that's shift 7 or whatever it is. Shift 6, sorry. Shift 6, so that's the power of operation. So we've got 2 to the power of 8 is equal to, 2 to the power of 3 is equal to 8, that's fine. To go backwards this way, that's also fine, because I'm just going to take the root of 8 and the number root is the other triangle, so that's fine. But now I need to work out what that question mark is. Okay, so the operation needs to be defined, and that's where logarithms come in. Eric. Oh, sorry. Yeah, right. So logarithm is where we're headed. And what I'm trying to do is I'm trying to explain why we need logarithms and where it fits into the whole pattern or into the whole sequence of mathematics, I suppose. So what is that question mark? Well, basically, we call it a logarithm, and that question mark is going to be a log, and we, just like what we've done in the other instances, we have used the other corner of the triangle in order to work out the undo. So we put the base down here like so, and it's this, in this instance, log base 2. Okay, so to go backwards this way, I'm going to use log base 2 of 8. So log base 2 of 8 is equal to 3. And that is just a definitional thing. By definition, if we say log to a certain base undoes the result to get me back to the power, then it must be that log base 2, 8 equals 3. It is just definitional work. Okay, so it's a new operation, just like you learned how addition works, subtraction works, multiplication works, division works. It's a new operation called log. Okay, and it is the second half of an undoing of a power. Okay, any questions on that? I'm going to zoom out in a second, but I just wanted to do this definitional stuff first, and then we'll collect it all together. So if a to the power of y equals x, this is the definition of a log, then y, the power, is equal to log base a of x. Okay, so this now gives us an opportunity to work out a power. So in the olden days, you would have a book, and in the book, you would have common logarithmic values, and you would consult the book to work out what the logarithm was. Okay, so we start, how do I put this? There are certain logarithms you could work out based on just your general knowledge of powers, but there are certain ones that you couldn't work out. And so in the olden days, you'd get out a book and you'd figure it out from the book. Even when I was a student at school, I would certainly be reaching for my calculator, not for my logbook. That was more in my dad's days. So there you go. So logarithms, are just a way of getting to the power, undoing a result to get to the power. Now, don't write this down, but I'll just give you a very quick example. So if I, for example, said log base 3 of 27, what I'm doing is I'm asking myself 3 to the power of what gives me 27? The answer is 3. So log base 3, 27 is equal to 3.
Does that mean you can say log base 3 to the 27 is equal to log base 2 to the 8?
Yep. Why you'd want to is another question, but you could certainly do that. Log base 4, 16 is equal to, Sam? Putting you on the spot. Yes. 4 to the power of what equals 16? 4 to the power of 2 equals 16. Okay? Good, good, good. I'll be nasty. No, hang on. Log base 4, 2. I'll take hands up for this time. All right. Yeah. 4 to the power of what equals a 2? The square root of 4 is 2, so it means 4 to the power of a half is equal to 2. Okay, so you can get decimal numbers, of course, and fraction numbers. And then you've got ones like this. No one's putting their hand up because 3 to the power of something doesn't work, does it? 3 squared is 9. 3 to the power of 3 is 27. But it doesn't mean there's no answer. It's 3 to the power of probably 2.8 or something like that. Okay? So that's when you'd get your calculator out and you'd work it out using your calculator. Now, if you've got one of these babies, whether it's Sharp or Casio, if you've got one of these babies, you'll probably find that there is no log base 3 button. Your GDC has a generic log button, but you'll see that your basic scientific calculator, it has log, and it has next to the log button, you'll see something that says LN, it's not an IN, it's an L. So it only has 2 log buttons. One is log, which is log base 10, and ln, which is log base e. It's called the natural logarithm. So later in the course, again, I know that most but not all of you have done Maths Extended, but later in the course, you'll learn how to convert from one base to another. So if I've got it in log base 3, can I convert it to log base 10? The answer is yes. There's a little theorem called the change of base theorem. What the change of base theorem allows you to do is change the base. So it's quite well named, isn't it, really? Yeah, unless you're a musician, in which case you might think you're just changing, from a 4-string to a 5-string or to a 7-string, I don't know. But change of base theorem is all to do with changing this little value here. Okay, so I just tripped over a couple of things here which I don't have notes for. So I might just put a note over to the side here. Okay, so if you don't see a base number, it usually means that it's log base 10. So log x means log base 10x. Is that okay? Okay, there's another one which I'll deal with later called the natural log. The reason why is because log base 10 is such a common logarithm to use. It's frequently, it's just to avoid writing down. It's to make it simpler, I suppose, to write down because it's so common. To make it confusing, though, that sometimes, depending on your field of mathematics, sometimes you might, field of science, sorry, in some instances, log x might mean log base ex. think, I'm not too sure, engineering or something uses log base E for some reason. Or doesn't make sense to me though. You'd think it'd be more of a biology or something. Anyway, so if I wrote them as functions, because this is what we're going to focus on today with a bit of work, then we would write f of x equals a to the power of x. Now this is our exponential function. I might just zoom out now because, no, I'll do this bit first. So this is just our basic exponential function, because you can see that this is kind of the opposite, really. So g of x equals log base ax. Now, I want to just spell that out a little bit. If I look at the inverse function, I'll just say it. That's equal to the inverse function of x. So log base ax is the inverse function to a to the x, okay? And I'll show you that it works. If I have f of x equal to a to the x, then we write y equals a to the x. Remember, this is how we do inverse functions, remember? We then swap the x and the y. And now by definition, y equals log base a x. Okay? So log base ax is the inverse function to a to the x. And that's a really important result to be aware of as well. That we now not only do we have a new operation, which is logs, we also have an inverse function for the exponential function. I should just point out, there we go, all four together now. I should just point out that remember that the conditions for a graph to be invertible is that it is number one, 1-to-1, number two, that it is onto. So every value of x maps to a single value of y, and all values of x map to all values of y. And we have that in the exponential function. Okay, every value here is unique. Every y value for every x value is unique. Every single x value is, in this instance, every single x value is accounted for. And every single y value, as long as y is greater than 0, is also accounted for. So for this, I don't think I've talked to you about this before, but for y equals a to the power of x, we have the domain equal to all real numbers, and the range is equal to y greater than 0. Okay, so every value for y greater than 0 maps to x, and every value of x maps to y. Okay, so it's 1-to-1, it's onto, therefore an inverse exists. Now we know that an inverse cuts through, well, reflects across the diagonal, right? Okay, so that's y equals x. So based upon that, and just do it in pencil, I'm going to give you a second or two, so maybe a minute, to see whether you can graph log base a of x, based upon your understanding of what an inverse function would look like. And again, just to remind you, an inverse function mirrors across the diagonal. So I'm going to pause the video here while I give you a chance to do that. So either you got there or you didn't. Now, I deliberately didn't give you much information, so don't stress about it too much if you didn't get there. There are actually two things you have to consider with the mirroring, not just one. One thing to consider is that an exponential graph isn't just a blue line, is it? It's a blue line, and I might zoom out so you can see this now, and a red line. That red line is your old pal, the horizontal asymptote. Okay, so that's y equals 0 is the horizontal asymptote. So not only does the blue line reflect, but so does the asymptote. And you've got to see this, and this is where the video is not going to be very good to see me doing this. But what you're doing is you're swinging the graph as if it's like that's a hinge. You're swinging it that way. So when you do that with the red line, it swings to be a vertical asymptote instead. Okay, so for a logarithm graph, I don't know why I pronounce it like that. For a logarithm graph, you've got a vertical asymptote. So if you didn't put in a vertical asymptote, and I wouldn't expect you to, do it now, please. So step number one, there's a vertical asymptote. It's not a function, obviously, the vertical asymptote. It's a relation. It's the relation x equals 0. Okay, you can see having a couple of different colors really helps here, right? I'm using 4 different colors just to try and get this sorted. No, I'll use 3. Okay, so I've got a vertical asymptote. So you've now got to stop referring to asymptotes as asymptotes. You've either got to refer to them as horizontal asymptotes or vertical asymptotes. You can also have diagonal asymptotes and stuff like that. But for the purposes of this this thing, we've got both horizontal and vertical. The next thing to do, so basically, when I mirror this now, again, like a hinge, this line here is going to swing over this, and it's going to end on this side here. Okay, so this part is going to map over to here, and this part is going to map over to here. Now you're going to find that I'm not the best drawer of graphs again, but we've got this thing where as we've got this thing going along here like so. It's probably a bit too, I probably should have it a bit flatter than that, but that's basically what we've got here. Okay, so we've now got, this is y equals log base a of x. Now, like I said to you before, remember that when we get an inverse function, what we're doing is we're swapping the mappings of all the values. So x and y swap over. Okay, so that means that this point here, which is 0, 1, will then become 1, 0, which means that this coordinate point here is 1. And we've got our first outcome for a log now, and that is log base a of 1 is equal to, so log base a of 0, no, log base a of 1 is equal to 0. Yeah.
Isn't y is equal to y is equal log?
What have I done wrong?
That's the one thing I don't get, because should it be f of x is a to the x? Because y is, it's like saying, because if you're saying y is equal to a to the x and y is equal to log a to the x, that's the same thing as saying a to the x is equal to log a to the x. If you get
I hear you. The answer is yes and no, I suppose. So the top blue line, I should have done them in different colors. The top blue line is f of x. The bottom blue line is f minus 1 of x. The y equals thing that you were saying there, for the purposes of the video, in case it wasn't picked up, it was just asking, should I be basically using different letters because they're 2 different functions. Really, what we're doing is we're saying, what is the relationship between the y values and the x values? The top blue line, the relationship is that the y value, or the y coordinate, is given by a to the power of x, and that's why I've got that function written next to that line. And then on the bottom, I've said the relationship for this line is that the y coordinate is given by log base a of the x coordinate. Really a fine distinction. So I absolutely hear what you're saying, but what I've written here is not that uncommon. So if I was labeling f's and g's or f of minus 1s or whatever else, yeah, they should be different. But if I'm doing it from the y equals, it's really more like a statement of the rule than, yeah, good question. I like that. It made me think about notation then. So you can see here, this is a bit messy, I apologize for that. You can see here that the domain and the range have also flipped. So the domain is now x greater than 0, and the range is equal to all real numbers. Okay? So the range, what that basically means is that it doesn't matter how far I go up or down this axis, obviously, beyond what I've been able to draw, if I go across, I'll eventually find the line. If I go down, I'll eventually find the line. For the domain, as long as it's above 0, I will eventually find the line if I go up and down. But below 0, including 0, I will not find the line. Okay, so the domain and range have also flipped, which is basically what an inverse function does. Okay, the other thing that I might just scribble in but then undo because I don't want to make it too messy is that we can also say, for example, that say what color shall I use? Just trying to get a color that will not interfere. That at 1, this would be A on the A to the power of, because A to the power of 1 is equal to A. So that would be there. And then I'd flip that around and say that this would be the value of A here. So at A, the Y coordinate would be 1, because log base A of A would be 1. Does that kind of make sense? Log base A of A is equal to 1. Okay, so we've now got two specific outcomes or results. We've got log base A of 0 and log base A of A. Okay, but I'm going to undo that because it then gets very messy. That the graph's messy enough as it is. But remember, every point is remapped. Okay, so I'll just zoom out again. Any questions about this before we move on to the next thing? I've gone a bit slower than I meant to, but that's because I spent too much time on the other stuff. So, transformations. Now that we know what the function looks like, note that I'm saying f of x is a logarithm graph. So you wouldn't just use f of -1. Remember, f of -1 simply means the inverse function. So in other words, a to the x is an inverse function for log, and log is an inverse function for a to the x. Okay, so they're inverses of each other. So the notation is just to say what I'm inverting from. So I'm starting off with f of x equals log base 10x minus 2 plus 1. So how we go about it? What we would do is we would consider what those notations would, how they would affect the graph. Okay, so first of all, oops, left with purple. What are our transformations here? There's two of them, there's just two. What are the transformations? Up and along, can we be more specific than that? We have done transformations, haven't we? This year, yeah. We did it in the functions unit, I thought we did. Okay, I'll spell it out. So we have a horizontal translation. Right by 2 units. Number 2, we have a vertical translation. Up 1 unit. So remember, those things that affect the input, the x's, they're always sort of counterintuitive. So x minus 2 means that everything is happening a lot earlier. So therefore, it goes to the right. Okay. So what does that mean? When we look at our vertical asymptote then, if everything's translated right by 2 units, it means our vertical asymptote is now translated across by 2 units as well. Okay, then we've got a vertical translation up by 1 unit. Okay, so what does that mean? It means that we're now going to go draw our graph in like so. And if we use a combination of these two ideas here, we can see that this point here is going to be, oh, hang on, I'll go back to this thing here. As you can see, if the vertical asymptote is at 0, this point here is 1 unit across. It always will be 1 unit across. Okay, so when I translate this graph, I'm going to go 1 unit across, but also 1 unit up because of this. Okay, so that means that the new point is going to be 3, 1, like so. Now, I haven't explained how we would work out the x-intercept there. There is no y-intercept. I haven't explained how to get the x-intercept, but at least you can sort of see from that graph how the point has translated across. Okay, so in other words, zoom up for myself, i.e. 1, 0 has translated to 1 plus 2 and 0 plus 1, which is 3, 1. Okay, so the point 1, 0, which is on the parent graph, the base graph, has translated to 3, 1. What do you think? Questions? Okay, sorry, that was a little bit more theory, a little bit slower than I meant to go, so I hope it wasn't too slow for people. So next, I won't get you to start now because it was just being a bit pointless, I think. Next lesson, so on Thursday, I'll get you to start by looking at exercise 9F, page 409, and we'll do some work on that, and then we'll start looking at a few more rules and stuff to do with logarithms. Okay, I won't let you go to at 9:30, but you can pack up ready to go when I tell you to.